Hello and welcome to the first video of the section. In the previous section we learned about global economic maps with open data. This section will be fully dedicated to spatial point pattern analysis. This first video is dedicated to provide you with a general theoretical background into what is a point pattern and what sort of analysis we can perform on it. During the course of the section we'll learn various techniques to analyze a point pattern from different perspectives, for example its intensity and spatial distribution. The final part of the course will be dedicated to find possible hotspots and test ways to model our point pattern using covariates. In this image we are shown the location of all the burglaries that happened in London in the month of December 2015. These data are distributed under the Open Government Licence by the UK Police. A point pattern like this provides the location of objects or patterns that occurred in the study region. The aim of a point pattern analysis is to study the distribution of these events to gain insights into the process that produced them. This is what is referred to as a point process. The point process forms the basis for the statistical analysis of our data, because what we see in this image is just one realization of this process in a specific area and in a specific month. However, our objective is to study the process in a way that allows us to predict future crimes in the same area or even outside the study region. Clearly, a point process does not produce events only in specific regions. However, we observe and record these events only in the study area for convenience. It's therefore of crucial importance that the boundary of the study region is known, because we need to know exactly where the events were not recorded. The assumption behind a point pattern analysis is that within this region all the events were recorded without exceptions. As for every statistical analysis, we always need to start by describing our data. For a standard numerical dataset, the first thing you'll do is calculate its mean and standard deviation. For a point pattern, we can calculate its mean center, which is simply a point identified by the mean value of longitude and the mean value of latitude. This is important because it identifies the centroid of your dataset. The mean center becomes very useful, for example, to calculate differences between point patterns. For example, in this image from the US Statistical Abstract from 2003, you can see the changes in the mean center for the population of the United States over several years. This clearly allows us to identify a shift towards west of the population. Another important statistic is the standard distance, which is a circle with a diameter equal to the standard deviation of x and y around the mean center. This parameter measures the average spread of our point pattern around the mean center. The issue with this parameter is that it does not capture any directional bias between longitude and latitude. To solve this issue, we can calculate the standard distance ellipse, which calculates the spread for both coordinates separately, and it is also rotated towards the direction of maximum dispersion. The output is an ellipse directed along the direction of maximum spread, and which dimensions depends of the standard deviation along both directions. After this preliminary analysis, another crucial point of a point pattern analysis is the quantitative description of the spatial distribution of the events in the study area. These may be randomly, clustered, or regularly distributed, and finding their distribution may allow us to gather further important details about the point process that created the events. For example, a random point pattern implies that there are no relation between events, meaning that each crime is independent from the other. A clustered pattern means that crimes are probably to occur when others had already occurred before. This is a very important realization. The simplest way to assess quantitatively the spatial distribution of our point pattern is by calculating the changes in intensity throughout the study area. Intensity is defined as the number of points per unit area, and if we compute this parameter for small subsets, we may have an idea of which spatial distribution fits our data. One technique we're going to explore for this purpose is the quadrat counting. This technique divides the study area into sub-regions that can be of various shape and sizes, and simply count the number of events in each sub-region. This allows for a very fast and simple test of the spatial distribution of our events. Generally speaking, you would expect to have more or less the same number of events per sub-region if your pattern is regular. whereas for clustered patterns you'd expect some areas to have a higher than average number of events, as you have in this image. Other techniques we're going to explore rely on measuring the distance distribution of a pair of events in the point pattern. Take a look at these three plots. On the x-axis we have distances r between a pair of points, while on the y-axis we have the value of the g function. Simply put, the g function calculates the ratio between the number of pairs that have a distance equal or below r and the total number of points in the point pattern. This means, for example, that in the first plot, 40% of the plots are separated by 0.04 degrees or less. The shape of this curve allows us to determine the spatial distribution of our point system, as you can see in this image. Once we have quantitatively identified that our point pattern is clustered, we can check to see whether some areas present a higher than average intensity compared to their neighbourhood. This can be done by calculating the kernel density, which basically computed the intensity of the plot pattern for a moving window of custom size, h. As you can see from this image, the size of the window greatly changes the resulting map. We'll see in the course ways to calculate the parameter h. As you can see, some areas present higher intensity compared to their surroundings, which are called hot spots. Other areas present lower intensity. These are cold spots. Knowing the location of hot and cold spots is crucial in a pattern point analysis. The final part of the section will focus on modelling our point pattern. This means we try to explain the local changes in intensity. Take this example for instance. Here, the intensity of the point pattern named BEI, which is a collection of location of tropical trees, is correlated with the slope of the area. As you can see from the plot, some spikes in the intensity of the point pattern are correlated with increases in the slope. This may help us predicting the location of trees outside the study area. To conclude this brief theoretical background, I'd like to draw your attention to some resources that I think may help you a lot in deepening your understanding of spatial point pattern analysis. Some are completely free, while the last two are books that I have in my collection, and I think are very well made. In this first video we learn some basic concepts that need to be clear about spatial point pattern analysis.